In this lecture, we're going to start discussing series. And let me remind you of the connection between series and sequences. So let's suppose that we have a sequence Sn. A series is defined as follows, or series associated with Sn. Is defined in the following way. Sum from n equal to 1 to infinity of Sn is defined as a limit when k goes to infinity of sums n from 1 to k of Sn. These sums, if you remember, are called partial sums of the series. So this is a kth partial sum of the series. Right, the basic idea here is that I want to add infinitely many elements of my sequence, and clearly I'm not going to be able to do it just by continuing to add, because there are infinitely many things to add. So I will never be able to compute this quantity. But rather than adding the terms, we're now formulating this in terms of limits. So if I add k elements of a sequence, that gives me a new sequence, an element of a new sequence of these partial sums indexed by k. And if a limit of a sequence of partial sums exists, then we would say that the series converges. So if the limit exists, then the series converges. Now, if, just to fix the terminology, if the limit is plus or minus infinity, then the series diverges. And otherwise, if you're not considering either of these two cases, the series does not converge. Okay, and let's do a couple of examples. Let's say example number 1. Let me formulate this example actually geometrically. Let's say we have an interval from 0 to 1. And I'm going to do the following. I'm going to put 1/2 here. So then I'm going to subdivide the interval from 1/2 to 1 into two pieces. So then the length of this interval is going to be 1/4. I subdivide the remaining interval into two pieces. So the first remaining interval is 1/8. Another subdivision into two pieces. The first remaining interval is 1/16. And then if I continue doing this, then the division point is going to get closer and closer to 1, right? And the length of the distance from 0 to the division point is going to be the sum of lengths of previous intervals. So, for instance, first interval is 1/2. Second interval, first and the second interval together will give me 1/2 plus 1/4, 3/4. The first three intervals will give me 1/2 plus 1/4 plus 1/8. That is 3/4 plus 1/8, whatever it is. And if I keep going like this, then at the end of the day, I'll be basically adding, once I allow this procedure to go to infinity, I'm going to see that the point, right, the subdivision point, with increasing number of intervals, the rightmost subdivision point is going to get closer and closer to 1, number 1, and number 2, the distance between the rightmost subdivision point and 0 is going to be a sum of 1/2 to the power n. So from this example, I can conclude that if I add up, starting from n equal to 1 to infinity, 1/2 to the power n, I should get 1. Right, so that's just a geometric intuition. Okay, so then if we look at this more generally, let's say now I want to add up sum from 0 to infinity, right? So far I looked at a definition of a series where initial index was equal to 1, but it's likewise can be anything else. I can start with n equal to 0 or n equal to 15. I can start adding terms of my series for n equal to 15 from any n, in fact. So this notation is going to be meaningful for any value of the lower limit here. Okay. Fine. So what about a series like this? Sum of q to the power n, right? So q is a number. And I want to find the sum of this series. So what is that? That I can formally write as 1 plus q squared plus etc. plus q to the n plus, and you just keep going forever, right? Because it's an infinite series again. So this series would converge if the limit as k goes to infinity of partial sums, sum from 0 to k of q to the n, if this limit exists. And you see that it is not actually very easy to evaluate this limit because this is a fairly complicated value, right? So sum from 0 to k of q to the n, how exactly are you going to take a limit of that? It's not entirely clear. So what we're going to try to do, we're going to try to simplify this circled expression and get another expression, the limit of which we will be able to take. So I'm going to consider a partial sum of this series, which I'm going to call capital SK, and that should be again the sum n from 0 to k, q to the power n. Or if I expand this expression, this would be q to the 0, 1, plus q to the 1, q plus q squared plus etc. And then the last term is q to the k. Well, would I be able to make this expression simpler? Let's try this. Let's try to multiply sk by q. So q times sk, this should be q times 1 plus q plus etc. plus q to the n, right? Then I can multiply all terms out by q. This will give me q plus q squared plus etc. plus q to the n plus q to the n plus 1. Right, so multiplying by q still retains all powers of q, except that they're all now increased by 1. Well, what I can do with this, I can observe that actually, sorry, it's not q to the n, it's q to the k. So q to the k, q to the k, q to the k plus 1. What I can see is that q to the k is both here and here. Q is both here and here. Q squared is both here and here. So in fact, any power between q to the 1 and q to the k, right, that I have present here is also present there. So what I can try to do then is to rewrite this in terms of sk. So I basically have all terms in sk, right? Again, sk is this. And this is almost sk, but it's missing 1, right? There is no 1 here. So sk minus 1 then, right? So the sum of first k terms is nothing but sk minus 1. And plus there is an extra term q to the power k plus 1. So plus q to the k plus 1. And now what I got is an equation for sk, right? Qsk is equal to sk minus 1 plus q to the k plus 1. I can subtract qsk from both sides and move 1 minus 1 plus q to the k plus 1 on the left side to give me 1 plus 1 minus q to the k plus 1 equal to q equal to sk minus q sk, or 1 minus qsk, which I can now solve for sk, right, because this is just an equation for sk. So therefore sk is equal to 1 minus q to the k plus 1 divided by 1 minus q. So you see that this partial sum then collapses to a simple expression in terms of q and k. And so therefore, what I'm supposed to put in here is going to be the limit k goes to infinity of 1 minus q to the k plus 1 divided by 1 minus q. Okay, so let's see what we should be able to say. So let me rewrite this here. So the sum n from 0 to infinity q to the n now must be the limit k goes to infinity 1 minus q to the k plus 1 divided by 1 minus q. And if I look at this, then basically what do I see? I see that in the expression under the limit, 1 minus q basically is a constant. 1 on the top is a constant, so really the only thing that depends on k is q to the k plus 1. So I just need to determine what is the limit of this when k goes to infinity. And let's see, what do we know? So actually, let me move it down here. So what we know is this, that if I take a limit when k goes to infinity of q to the power k. What should I expect? We have already showed that there are several possibilities here. So if, and that is a theorem from the section on properties of limits. If absolute value of q is less than 1, then this limit is equal to 0. So 0 if magnitude of q is less than 1. Now, if q is 1, it's exactly equal to 1, then of course this limit is, and you just get 1 to the k, so the limit is 1. If q is equal to minus 1, then what we get is minus 1 to the k, and that's a series which we investigated ad nauseum already. So then the limit does not exist, right? Because limit of minus 1 to the k does not exist. So dne if q is equal to minus 1. And actually, if q is less than minus 1, so then in magnitude, your q is bigger than 1. So if I raise q to the power k, then the size of q to the k will increase. And the sign is going to oscillate between minus 1 and 1. So that means that the limit actually is not going to exist because of oscillations. So this last statement then applies whenever q is less or equal than 1. And lastly, if q is what is the remaining choice, it's q greater than 1. So if q is greater than 1, then the number greater than 1 to the power k, we showed it before, this goes to plus infinity. So let me just move this now here. So the fourth possibility is infinity, and that is if q is strictly greater than 1. Okay, so we have all of these choices here. And now the question is, what should I expect up here? Well, again, the only choice, the only dependence on k comes from q to the power k plus 1. So that means that that will determine the behavior of the entire expression. So what is this going to be equal to? So if q is, magnitude of q is less than 1, then we said that q to the k must go to 0. And like we have said several times before, if I look at q to the k plus 1, basically it's the same thing as q to the k. The limit is exactly the same as the one for q to the k because you go move along the same terms as you go along the sequence, except that you're staying one index ahead than you will be where you will be when you walk along q to the k. So the limit must be exactly the same. So if magnitude of q is less than 1, would expect that this converges to 0. And if this converges to 0, the only thing that remains is 1 over 1 minus q. And that is a constant independent of k. So then the first choice, we get 1 over 1 minus q. And that is if q in magnitude is less than 1. Okay, so next, if q is equal to 1, then we are in trouble because if q is equal to 1, then we have 1 minus q divided by 1 minus q. Both are equal to 0, so at q equal to 1, this formula does not make sense. The formula does not make sense, but let's go back to the definition of Sk. So Sk is a sum from 0 to k of the elements of your sequence or your series. But in this case, q is equal to 1, so all of these terms are going to look like 1, 1, 1, 1, 1, 1, 1. So in that case, Sk actually is equal to k, right? Because you're adding 1 to itself k times, and the limit of k as k goes to infinity is infinity. So the sum of the series is going to be infinity if q is equal to 1. And in fact, if we look now at the last case, if q is, sorry, it's not bigger than 0, but bigger than 1, the last case, when q is bigger than 1, the limit of q to the k plus 1 is going to be infinity again. And if q is bigger than 1, then 1 minus k is negative. So you have a large negative number divided by some negative number. So Sk then is a large positive number, and as k goes to infinity, Sk goes to infinity. So infinity if q is bigger than 1. And if q is less than 1, then the limit of this quantity does not exist, so therefore the limit of the entire thing cannot exist. So does not exist if q is less than 1. Now, just a piece of a terminology, which again you might remember from Calc 2. This is called the geometric series. Q is a multiplier of a geometric series. And so then the conclusion is that the series converges, right? The sum of a series is finite and equal to 1 over 1 minus q if magnitude of q is less than 1. Otherwise, the series either diverges if q is bigger than 1, or it does not converge if q is less than minus 1, not less than 1, sorry. Right, because that is the situation we encounter here. In fact, less or equal to minus 1, sorry for these errors, less or equal here, and less or equal there, because both for q equal to 1 and q bigger than 1, the sum is going to be infinity. So the geometric series converges only if its multiplier q is a number which is less than 1 in magnitude. And then if we go back to my geometric example, then this is a geometric series with q equal to 1/2, so it has to converge. And it has to converge because of what we said down here. And what is the sum of this series? So we know from geometry that the sum is equal to 1. Let's see what we're going to get from the formula. So sum n from 1 to infinity 1/2 to the n. And then according to the formula up here, this should be equal to 1 over 1 minus q. That's 1, over 1 minus q. Q is 1/2. So 1 over 1/2, 2. And that's a different number that I got here, because here I got 1. So what is the problem? The problem is that the formula that I got is for the series that starts at 0. So if I add q to the n starting from n equal to 0, I'm going to get this 1 over 1 minus q. But when I start from 1, what is the difference? The difference is that when I start from 1, I'm not including the first term with the index n equal to 0. What's a term with an index n equal to 0 here? It's 1/2 to the 0, 1. So 1 is not included in the circle expression, but it is included in 1 over 1 minus q. So to get the correct answer, I need to subtract the term that I did not include in the series here, right, versus this series. And then 1 over 1/2, 2 minus 1, 1. So this verifies my computation in the first example. Okay, so the moral of the story is if you see a geometric series, then the geometric series is always going to converge at modulus of q, the magnitude of q is less than 1, and you have a precise expression for what the sum of the series is going to be. Okay, so let's try another one. Number 3. Sum n equal to 2 to infinity. Let's say 5 to the n minus 1 times 3 to n plus 2 divided by 2 to the power 2n. And the question is, does this series converge? And if yes, what is the sum of the series? All right, let's see. So at this point, we only know how to deal with geometric series. So maybe this series is going to end up being a geometric series. I just need to manipulate it a little bit so that it does look like a geometric series. One thing here, let me make this 4n. So how can I make this a geometric series? Let's look at the expression. So it's 5 to the n minus 1 times 3 to the n plus 2 divided by 2 to the 4. And I want to be able to write it as something times something else to the power n. So what kind of things do I have to the power n here? I have 5 to the power n minus 1. So it's 5 to the power n times 5 to the power minus 1 times 3 to the power n times 3 squared divided by 2 to the 4n is 2 to the 4 to the power n. And so then let's see, without n we have 3 squared 9 times 5 to the minus 1, so that's 9/5. And then we have 5 to the n times 3 to the n divided by 2 to the 4, 16 to the n. So the whole thing is 9/5 times 15 16th to the n. So that means that my series looks like this. Sum from 2 to infinity of what I had over here. This is the same thing as a sum from 2 to infinity of 9/5 times 15 16 to the n. Now, if you follow the proof above, or we will show this later on when we discuss properties of series, but I'm going to use that property right now. What can I do if I have a sum of a bunch of terms and I'm multiplying each term by the same factor? Then clearly I should be able to factor this out. Again, we'll prove this later on. So if I factor this out, then I get 9/5 sum from 2 to infinity, 15th, 16th to the power n. And that is a geometric series. With q that is equal to 15/16th. In this case, I don't need to take an absolute value because q is already positive, so it's less than 1. So therefore, the series converges. Because I'm actually dealing with a geometric series with appropriately small q. So now, you always hope that the series does not converge, because if it does not converge, then I cannot ask you to find the sum of a series. In this case, the series converges. So I want to be able to find the sum. And so let's look again at this new expression that we got. So this is what we need to compute. And again, recall that I have a formula for sum of q to the n. It's 1 over 1 minus q. But that sum will have to start from 0. So that means that I have to rephrase this as a sum starting from 0. So this is going to be 9/5 sum, and from 0 to infinity, 15th, 16th to the n. But I actually need the sum not from 0 to infinity, but from 2 to infinity. So that means that I need to remove from this the first term. When n is equal to 0, that's 1. And then I need to remove so I'm removing a 0th term and the first term. So minus 1 minus 15th, 16th. Okay? So then what this gives us is 9/5. Sum from 0 to infinity of q to the n is 1 over 1 minus q minus 15th, 16th, minus 1 minus 15th, 16th. Let's see how much that is. That is going to be 9/5 times 16 minus 1 minus 15, 16th, whatever it is. The point being is that I am able to compute the sum, again, starting from any n, because I just need to subtract the first few terms that are present in the formula over here, but they're not present in the actual sum that I'm computing. Now, one other point that I want to make here, which is going to be valid in the subsequent chapters, if I start adding the elements of my series starting from any finite number, so from n 10,000, from n 2, from n 15, keep in mind that this should not affect the properties of convergence of the series. Why? Because adding few elements of a series is not going to affect the behavior of a series or of a sequence in a tail, right? So for the convergence of a series, what is important, what terms are doing in the tail of a series and not in the beginning. So less or more terms in the beginning should not affect the convergence of a series. So when you're talking about the convergence of a series, you just need to understand what is going to happen with the sum of a tail terms of your series. And we'll discuss this more later on. In the meantime, two more examples. Number 4. Let's say I want to answer the same question as in the previous example. I want to determine if this series converges, and if it does, then what is its limit? What is its limit? Well, let's look at the sequence of partial sums. S0 is minus 1 to the 0, that is 1. S1 is going to be minus 1 to the 0 plus minus 1 to the 1. So that's 1 minus 1, 0. S2 is minus 1 to the 0 plus minus 1 to the 1 plus minus 1 to the 2. First two terms cancel just like in the previous line, and then there is also an extra minus 1 squared, so that is 1. One more, S3, minus 1 to the 0 plus minus 1 to the 1 plus minus 1 to the 2 plus minus 1 cube. Well, again, I know that the sum of the first three terms, the same as S2, is equal to plus 1, then minus 1 cube is minus 1 plus 1 minus 1, 0. So already see the pattern that S0 is 1, S1 is 0, S2 is, so S0 is 1, S1 is 0, S2 is 1, S3 is 0. So you can use induction to show that actually S with any even index is 1, and S with any odd index is going to be 0. So, but then does the limit of the sequence of these S's exist? So limit n goes to infinity of sk, limit of a sequence of partial sums, in this case does not exist because a sequence of partial sums will oscillate between 0 and 1, right? Original sequence oscillates between minus 1 and 1, and this new sequence oscillates between 0 and 1. So limit does not exist, right? Limit of partial sums does not exist. So the series does not converge. All right, so this might indicate that whenever you have a series with alternating signs, it's not going to converge, but you will see later on that that's actually not necessarily the case. So the final example here is that of a harmonic series, and let's talk about it a little bit. So this series clearly consists of all positive elements. So if you consider its partial sums, the more terms you add, the larger the partial sum is. Which means immediately the partial sequence of partial sums must be increasing in this case. And if it is increasing, then as we know, any sequence, any monotone sequence, either goes to monotone increasing sequence, either goes to plus infinity or converges to some number. So somehow we have to decide which one it is, convergent, whether this is convergent to some number or goes to infinity, and that should be somehow indicated by how fast the terms of a series are going down to 0 with n. If they go to 0 fast enough, then you're not adding too much on the next step, on each next step, and the overall sum is finite. Or if you're adding too much, then the overall sum will go to infinity. And let's try to analyze what we got here. So if I look at just 1, so observe. Of course, 1 is greater or equal than, simply greater actually, than 1/2. 1/2 is greater or equal than 1/2. The next two terms are 1/3 and 1/4. So if I take 1/3 plus 1/4, then I see actually that this is greater than 1/3 is bigger than 1/4. So this is greater than 1/4 plus 1/4, which is 1/2. I keep going like this. Next four terms are going to be 1/5 plus 1/6 plus 1/7 plus 1/8. And now all terms 1/5, 1/6, 1/7, they're all greater than 1/8. So this is bigger than 1/8 plus 1/8 plus 1/8 plus 1/8, which is again 1/2. And then the last observation here. So the next 8 terms are going to be 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. And in this sum, every term is greater than 1/16, greater or equal than 1/16. So overall, the sum is going to be bigger than how many 1/16? Bigger than 1/16, bigger than 1/16, bigger, 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 bigger. So 7, 8. So this should be greater than 8 times 1/16, which is actually 1/2. And so now what I can see is that if I add all the terms of my harmonic series, then terms actually are never exhausted, right? Because this is an infinite sum. So the first term is bigger than 1/2, second term is bigger than 1/2, next two terms are bigger than 1/2, next 4 terms are bigger than 1/2, next 8 terms are bigger than 1/2, the next 16 terms, if I add them up, will be bigger than 1/2. And this will continue infinitely many times. So that means that my series from 1 to infinity, so then the conclusion is that the series from 1 to infinity of 1 over n must be greater than a sum of infinitely many 1/2s. And the sum, if I add the same term to itself infinitely many times, I'm going to get infinity. So that means that the sequence of series of 1 over n's is going to diverge. So the harmonic series diverges. Okay, and so then in the subsequent lectures we're going to look at look at and prove various tests for convergence.